Good afternoon, everyone. Thanks for coming to this session. Really appreciate that you take the time today to come and visit us in Mandela Bay, which is on the other side of the strip. So hopefully you get what you came for. My name is Adrian Hornsby. I'm part of the Resilience organization. I'm principal engineer. We own the Fault Injection Service. I'll be joined today by Uliana, who is an engineer in our team, and by Lex, who is part of the BMW Group, and he's going to come and talk about their journey with chaos engineering. So, show of hands in this room, who is doing chaos engineering today? I'm talking chaos engineering, not just chaos. Right? So, chaos engineering, anyone? Okay, and from those doing chaos engineering, kind of what's the maturity level? Are you like starting the journey, up, and advance in the journey? Yeah, so it's actually quite reflective of the last 9 years of me doing talks about chaos engineering. There's a lot of interest and still very few people doing it. And it really just shows that it's not really trivial. So I'm gonna talk a little bit first, what is chaos engineering, and then we're gonna ramp up and do some demos and things like this. So the official definition of chaos engineering is really that it's a discipline of experimentation, and we inject fault in the system to gain confidence in the system ability to recover from turbulent condition, right? So that really is the standard definition. It's good, but I much prefer to think about a methodology to verify our assumptions. I mean, we are humans, right? Our systems are mostly human systems. There's some technology, but a lot of it is humans. And humans have tons of biases, right? When we build systems, when we operate them, we have biases all over the place, whether it's confirmation bias, availability bias, proximity bias, all these, they completely affect what kind of decisions we do. If you've had an outage in the last 2 months, I can guarantee you that the next design docs you're gonna do are gonna be so focused on what you just gone through. And if there's new technology, we have typically a bias towards using what's fun and new. We're engineers, we love this kind of stuff. So basically, all our systems are filled with biases. And chaos engineering is very, very nice to make us double-check our biases, right? And verify the assumptions that we do. Because you can't lie with data. You can't lie with how the system reacts and the metrics, right? And really, this is critical. And just to show how much our assumptions are guiding our designs and systems, are there any Python developers in the room here? Python developers, show of hands. Okay, so you know the request library. It's a library to do HTTP requests against endpoints, and they have a default timeout. What's the default timeout of that library? Is it 10 seconds, 30 seconds, 1 minute, infinite? Well, it happens that it's actually no timeout. The default is there's no timeout. So if you use that library in your system and you haven't checked the timeout, that means your connections to the database, for example, will just stay open forever until hopefully the database or your systems or your dependency, time out themselves. But if something happens on your dependency, that's it. You've lost that connection. And that really is critical. Another one, any .NET developers in the room? .NET? All right, so there's the web request methods. Default timeout, 10 seconds. Oops, sorry, I went too far. The default timeout, 10 seconds. 30 minutes, infinite. Well, it's 100 seconds, so almost 2 minutes. And in the time of distributed system, 2 minutes is infinite, right? Tons has happened. You have a retry storm that have happened, that's it. Humans are patients for typically 7.5 seconds, right? So if you don't have a timeout and your users are retrying, that's it. It's, going to do that at scale. And if it's a distributed system and you have millions of users, that's it. Your system is going to be taken down by just a timeout at 100 milliseconds. Typically, you want to have timeouts within the hundreds of milliseconds, right? 200, 300, depending on your system, sometimes much shorter. And last one, are you using the MySQL connector? What's the default timeout? Come on, that's a database, right? It's used often. You're using MySQL, anyone? MySQL? Okay, what's the default timeout? 10 seconds? 2 minutes? Infinite? And it's not defined 0, infinite. That's a database connector. All right, you get the point, right? Assumptions are really at the heart of many of the outages we have. And this is why it's so important that we take care of them. Never assume, go and verify, right? That really is the case. And now if you think about it, our systems is, tens, hundreds of dependencies, packages, all of them have defaults. Whether it's a timeout, it's a whatever it is, there's default value. Somebody that built that package, that built that library, said, I'm going to put a default, and they had no idea about the requirement of your systems, right? So if you don't go and verify them, you're going to have problems. Now, when you have hundreds of dependencies, I can guarantee you, you're not going to go one by one and verify them. And even if you do that, it's going to take time, and you're going to forget. And really, the best way to do that is go and test the system and inject some fault and see what really happens, right? And that's the heart of what chaos engineering is, verify your assumptions. How many of you have basically become senior engineers because of outages, right? The biggest lesson we have is typically outages. I remember mine, typically my entire life is failures, right? That's what I talk about all the time. How many of you have had so many outages that you think, it made you a senior engineer? Yeah. So I can guarantee you, the more outages you have, the more senior engineer you're going to become. And the problem is, like 10 years, 15 years ago, our systems were, not so resilient, not so reliable that we had a lot of time to practice our recovery skill. We knew our command line by heart. It was just maybe 60, 70% of our teams was doing operation in the cloud. That was the standard things. Like we didn't have auto-scaling, we didn't have managed services, we didn't have all that. That's all work we had to do. But now systems have become a lot more resilient. So that means you can go months without an outage. And you know what happens if you don't practice your skills in month? You get skill atrophy. That means you forget. And forgetting, it means that it's going to take so much more time for you to figure out what to do when the problem happens, right? So doing chaos engineering is actually what I think a compression algorithm for experience. It makes you continuously practice your skill, discover a new one, and make sure that you don't lose your craft, right? And we've used that quite typically at Amazon. And I'll talk a little bit about that. So why should we care about all that? Right? I've given some example, but as a business, why should we care? Well, a big part of why we do that is because the cost of outages is completely incredible. For 90% of enterprise, the cost of outages is roughly $300,000, right? And for 41% of this enterprise, it goes between 1 to 5 million per hour of downtime, right? That's not me saying that, it's actually research and from 2024, right? So this is the latest data. And companies that practice recovery pay 16 times less per hour of outages than companies that do not. So there's really a lot of incentive for companies to recover faster. And what's the best way to recover faster is to practice recovery. If you look at that graph, right, it's actually the anatomy of an outage. Right? You have the detection, the evaluation, response, recovery, and confirmation. If you look at that, the 4 steps on the right, so from the evaluation, response, recovery, confirmation, it's very much human-driven processes. And again, it's things we need to practice. Right? The longer you spend time doing that, the longer your outage and the more costly it's going to become, right? And that's very, very critical. Good. So we've done actually chaos engineering, some form of chaos engineering at Amazon since the early 2000s. It was a chap called Jesse Robbins. And Jesse Robbins, who is in the picture here, was a firefighter. That was his career. And he was, his title was Master of Disaster, which is pretty awesome title. He used this experience as firefighter to actually start a program called Game Days. And Game Days at Amazon is a program where we use chaos engineering to go and practice our recovery skill. And he used that to really train the operation team to recover fast, right? And that's since the early 2000s. Today, we still do this, actually, for every feature launch, for every services, we have something called the Operational Readiness Review, and that review mandates us to do those game days. So something we do very regularly. And if you want to learn more about those game days at Amazon and the origin and how they were planned, I've attached the link to the presentation of Jesse Robbins from 2011. And it's absolutely incredible presentation, so I highly recommend everybody to go and check it. Another reason to do chaos engineering is obviously regulation. Actually, in the last few years, we've seen a very large influx of financial services getting into chaos engineering. Actually, you can even argue that they are really at the forefront of advancing chaos engineering now because regulations are forcing them to do that. Actually, in Europe, DORA comes into practice next year and mandates that all those companies do those resilience exercises, including chaos engineering, disaster recovery, and all that kind of things. So now there's a very large amount of companies that fall under those regulations, and including automotive industry as well, and which is one of the big reasons that BMW also went into chaos engineering. So if you're in regulated area, it's definitely something that you should pay attention to. One very important thing about chaos engineering to understand is, and it is very different from standard projects that have a start and end date, is that it compounds over time. Right? It's not something you start today and you end in 6 months and that's it, you've done chaos engineering and it's good. It's actually a continuous thing. It never stops. So you should really see chaos engineering as the same way we see cybersecurity nowadays, as a continuous effort, part of the strategy, and that's actually very, very difficult. BMW, so Lex will share some tips how they got leadership support to really encourage this kind of long-term planning and long-term view of chaos engineering. But this is typically the maturity, how companies get into chaos engineering. There's obviously the initial adoption, and then learning and doing what's called an FMEA, so failure mode and failure mode analysis, right? And that's really, really critical. Actually, you could debate that most important part of chaos engineering is the before and after. The experiment is great, but most of the learnings happen before and after. So the failure mode analysis, failure mode effect analysis, and then doing a post-mortem after an experiment, this is really where learning happens. But this is the typical way a company adopts chaos engineering. We're going to focus today on ad hoc experimentation and game days and eventually continuous experimentation. Uliana will do some demos about this. But I want to talk a little bit about the failure mode analysis because that's such a critical part of getting started and figuring out what kind of experiments we want to do on our system. And there's like tons of different categories of failure. But when I work with teams in AWS and we do our operational readiness review, I like to think about these 3 categories of failure because I think they give us a very nice framework to think about potential problems in our systems. The first one is fault isolation boundary. That really is what defines the potential blast radius of an application, is how far or how contained the failure is gonna be, right? You've heard the butterfly effect, right? So fault isolation boundary is really to contain this kind of cascading failures where a failure in, for example, one container could impact a full cluster and then a full service, so really like through cascading failure. And thinking about fault isolation boundary is absolutely critical when you design your application. Therefore, it's critical when you're gonna think about chaos engineering and what kind of experiments you want to do. And we'll talk about this quickly. The second is obviously dependencies. And I've talked about timeouts. So dependencies are all the time part of our outage repertoire. And it's never gonna stop. There's more and more dependencies, and it's not just a third-party dependencies through an API, it's also just a package, right? When you do an NPM install, or you download tons of packages, right? All these are dependencies that comes with their own default, their own problems, and it's stuff you're gonna have to deal with eventually. And then bimodal behavior, this is probably my favorite one, it really defines or try to understand how a system under different conditions may operate very differently. The best example of that is a cache system, right? When you have a cache system, typically you have a request going to the cache. If you have a hit, it returns the value, right? That's one mode of operation. But if the cache is a miss, or if the cache fails, you go to the database, and that's a second mode of operation, right? The same request might have 2 modes of operation, and your system is once very latency efficient on the cache, and the other one will be less performant and tapping into the database, right? So very different modes of operation. So when we design our system, it's super important to keep that in mind and design experiments that go and trigger those different modes of operation. Today, this is the diagram of the application we'll work with in our demo. It's fairly simple architecture. I'm sure you're all familiar with EKS or Kubernetes. So this is the managed Kubernetes, so EKS, which has an auto-scaling group included. It's basically an architecture made across multiple AZs. So you have your instances there. There's some VPC endpoint to access the database, and then you have a cache in the middle, right? So Elastic Cache is basically your ephemeral data layer. DynamoDB is gonna be your persistent data layer. And then you have an application load balancer that takes traffic and distributes traffic across multiple AZs. So if we take our failure mode analysis and we do the fault isolation boundary, dependencies, and bimodal behavior, what kind of fault isolation boundaries, the obvious ones that we have here that we need to test for? The AZ isolation definitely is going to be, and is one that is on top of the mind of most customers. What else? Come on, try. There's no bad answer. Huh? That's a bimodal behavior, right? So Elastic Cache is going to give you a bimodal behavior depending on the cache hit and miss. Yeah, definitely. What else? Huh? Definitely, that could be also fault isolation, right? So if in that case you would have a multi-region system and there's a region impact, will it impact the other region? Right? So do you have a dependency back to the other region? That's definitely something that customers that have multi-region workload want to verify through chaos engineering. So There's few others, right? The most obvious one, the most thing that people don't think about, a process, right? The container, they're all fault isolation, right? A process, if it fails, it needs to be contained, the failure, within the process space, right? It shouldn't kill the container, it shouldn't kill the cluster, it shouldn't propagate, right? So you have to start really, really, really small. You also have the auto-scaling group, right? That's a clear fault isolation boundary that you want to test for and see that, what happens if you impact the auto-scaling group and you inject some fault, like for example, some capacity errors, right? And something that might happen with Spot or things like this. On dependencies, we obviously have DynamoDB, Elastic Cache, but there's some hidden dependencies here. You probably have IAM policies, right? IAM. You probably maybe have KMS that encrypts the data in DynamoDB, right? And very often, diagrams don't have this kind of dependency. So it's something you need to surface and think about when you do your case experiments and classify your dependency in terms of obvious, hidden, things that are actually on every request, things that are just on the initialization phase of the application, so the boot time. There's tons of things like this that I have to, definitely. Secret manager might be one of them, app config, to distribute configuration. So there's tons of dependencies like this that we want to work for. But I'm gonna welcome on stage Juliana to actually go and show us hands-on what it do all that. The floor is yours.
Thank you very much. Hi, everyone. Thank you. Okay, so it's time to see the chaos engineering in action a little bit. So I'm going to start from the ad hoc experimentation. So ad hoc experimentation is a straightforward approach to uncover those unknown unknowns in the application. And I'll tell you, when I just started preparing for this demo like months ago, I was thinking like, what application should I build to show you those great chaos engineering experiments? And what I discovered is that chaos engineering helps me actually not just test my already existing application, but also to learn a new technology, because I chose an EKS, a Kubernetes service for this demo application, and I wasn't very much familiar with that. So I was continuously doing this ad hoc experimentation, was continuously running those chaos engineering experiments, and I really learned a lot about the technology. So that was the power of chaos engineering. So now let's start for the ad hoc experimentation. I'm going to use the architecture that Adrian already described, which is let's say the example product catalog application with the get and put API endpoint. So let's dive into it. I'm going to start from the defining a steady state. And why do we need to define a steady state is simply just to compare how the application behaves before we run the chaos engineering experiments and how it behaves during the chaos engineering experiments. So we can identify if something goes wrong. So here I go to the operational health dashboard of this application that we saw. We have this customer metrics first. These are the business metrics, and the first one is the alarm widget for the high latency for the get product API. And the important thing to know here is that the latency is way below the threshold, which is great, steady state. The customer success rate for this endpoint is also 100%, and the cache hit rate is 100%, meaning that the data completely is retrieved from the cache. Here we can see an interesting thing. The query latency to DynamoDB, which is the persistent layer of the application, doesn't show any data. And this means that the bimodal behavior of this GET request API works perfectly. The data is only retrieved from the cache, and DynamoDB is not invoked during the normal operations. So this is the steady state. Now we move on to the identifying those assumptions that we would like to verify during the chaos engineering testing. So what is the assumption? Let's go back to this architectural diagram. So here we can see the application load balancer, 3 availability zones, and then we can see the Elastic Cache and DynamoDB. So the GET request API goes to and tries to fetch the data from Elastic Cache. If the data is not available in Elastic Cache, we go to DynamoDB, something that Adrian already described here. So this is exactly the assumption that we would like to test and see if this is the behavior. What we are going to do during our ad hoc experimentation is to inject additional latency from the pod, my Kubernetes pod, when it makes the request to the Elastic Cache. If you inject the latency, let's say the latency will be too high for me because my acceptable latency is 2 seconds. I'm going to inject 10 seconds latency to Elastic Cache. So the behavior I expect is that the request should go to DynamoDB and get data from DynamoDB. So let's verify if that's true. So I'm going to use the Fault Injection Service tool to run this chaos engineering experiment. Is anyone familiar with Fault Injection Service tool? Yeah? Okay, we have some people. Good. So we will start from creating the experiment template. So experiment template is nothing but the configuration of your chaos engineering experiment. So I go ahead and create this experiment template. I give it a description, and then I go and configure the action. The action itself is the fault that I'm going to inject. And as we already discussed, it's a pod network latency. I configured this experiment to be run through 20 minutes, and then I configured the necessary permissions for the Kubernetes to run this experiment. Then the latency that I'm going to inject is 10 seconds, and then we can see in the sources, this is the endpoint, cache endpoint. And this is exactly the endpoint that the latency is going to be injected into. Here, we are configuring the target. So the target is actually that cluster and the pods which are going to be under the fault injection. So here, the label that I select is up reinvent. This is the label which is attached to the pods. So this is how they are going to be resolved during the experiment execution. The next thing I configure is the permission for the experiment. I selected admin role. Don't do this in production. It's just an example for the demo application. And here are the logs, just to put the logs of the experiment execution. And here we are done. We created the experiment template, which is the configuration of the ad hoc experimentation. Once it is created, we can start the experiment. So at this point, we can see that the experiment moves to different steps, and once it's running, we can say that the fault injection is running. We give those 20 minutes for the experiment to complete, so we allow our application to fully react on the fault injection, and then we will see what happens. At this point, we move to the analyze step. During this analyze step, we will just go to the operational health dashboard and see what happened during the fault injection. This is an interesting part. Okay, so the experiment is completed. We check the customer metric, and we can see that the latency is so high. It is at 10 seconds, which is way higher than the threshold. And the alarm is on fire. Yeah, it was a fire. So customer success rate is not that good. And what is interesting here, the most important part, is that DynamoDB query latency still doesn't show any data, meaning that the assumption was wrong. The GET request API didn't go to DynamoDB. It was still waiting for the cache to respond, because we can see that cache hit rate was still 100%. So this is a problem. It means that the assumption that we were going to test was incorrect. It was never assumed. Okay, so now an interesting part to investigate. So I'll go here and I'll stop for a second. Any ideas why the issue happened? So the request was waiting for those 10 seconds, and only after still was getting data from the cache. Why it didn't go to DynamoDB? Timeout, nice, yes, exactly. This is the I go to the code because I know exactly that I need to check the Redis client, which is in my case the client, and I can see I don't have any parameters for the timeout. So I check the documentation of the Redis client. And what I can see here is that both timeout properties, they are set to none, meaning that the request will wait whatever it takes in order to get the data from cache. In our case, it was waiting those 10 seconds, because this is the latency that was injected during the experiment execution. So what I do, I set these two properties to, let's say, half a second, because this is acceptable for my demo application, which is 2 seconds is my threshold, so half a second is fine, and I redeploy the application. At this point, we are moving to the last step to repeat the process again, in order to verify if the fix was working, and maybe to learn something else. So I go to the same experiment template, it's already created, and I just run the experiment again. We again see that the experiment moves to different steps, and once the experiment is in the running step, we again give the experiment those 20 minutes, so the application fully reacts to the fault injection. And when it's completed, let's go to the operational health dashboard and check the result. So here we can see the metrics for both experiments. The first one was latency was super high, but during the second execution, the latency was actually normal. It was below 2 seconds because we introduced the timeout. And then to verify that this bimodal behavior of the GET request was working properly, we go to DynamoDB query latency, and we can see the metric is there, meaning that the data was retrieved from DynamoDB. And when we check the elastic cache hit rate, it is at 0% during the experiment execution. So this means that the experiment worked, the application actually behaved the way we expected it to behave after the fix was introduced. So this is a quick example of the ad hoc experimentation, how you have an assumption, you go to your application, you go to Fault Injection Service tool, run the experiment, and then see what the result we have. So at this point, we are done with the ad hoc experimentation, which doesn't require much knowledge. But we will move on to the more comprehensive approach of the chaos engineering, which is game day. Adrian already mentioned the idea of a game day, which is a periodic process of testing the runbooks, verifying that the alarms are in place and are properly configured, verifying that the on-call personnel can actually follow the runbook in order to understand where the problem is when the issue happens. So today I'm going to show you a quick end-to-end process of a game day, the way it would probably work in organization who wants to start with the game day. I'll start with the game day process. The game day process is, let's say, it's just a document. This is the example document which I created for this demo application. And this document just describes what we want to get out of a game day. It has a planning stage, execution, and the analysis and report. During the planning stage of the game day, we would like to describe what we actually want to do during the game day. In this case, we would like to check the fault isolation. So we are going to have the availability zone impairment using the AZ availability power interruption scenario, which is available in the Fault Injection Service. This scenario is just an already predefined experiment template with all the resources that exist in the availability zone. The action here, it would be to inject the expected symptoms of a complete interruption of availability zone. And the assumption that I form during this planning stage is that I shouldn't see any customer impact, because this was the idea of building multi-AZ application, right? Even though one availability zone is impaired, I still have 2 healthy availability zones. So this is the assumption, so let's see during the game day if that's true. During the execution stage, we describe how we should run the game day. And this is the command, which is AWS FIS CLI command to start the experiment. Running this experiment, running this command will actually kick off the game day. During the analysis and report is the post after the game day was run. We define what were the outcomes and what did we learn from the game day. So this is the game day process. The next step is, of course, to go and check what is the steady state of the application. So again, we can compare. The steady state of the application is that we have this customer metrics again for the get product and put product API. The metrics are high internal failure rate, and we can see that they are in the steady state. The customers, imaginary customers of this demo application, they are happy. Then customer success rate is at 100% for both APIs. Cache hit rate is at 100% as well, meaning that the application works properly. And then to the right, we have these 3 groups of metrics. And these metrics are grouped by the availability zone. Each group is how many healthy targets we have in every availability zone. We can see there is 1 healthy target in every zone. Okay, so this is the normal state of operations of the application. So at this point, we can move to the next step, to actually play. Play is to run a game day. And this is probably executed by the chaos champion, or how in AWS we have a secondary on-call, the person who will execute the game day in order to see, to measure what was the, how the on-call, primary on-call responds to the events. So let's go and start the game day for this example. I took that CLI command that was in the game day process. I started the experiment, so that kicked off the AZ impairment experiment execution. So I took that ID from the response in order to search for that ID in the FIS tool, and now I'm checking the resources. So this is the resources that are available in my application. Now I go back to the operational health dashboard, and I can see again, I see the alarm is on fire, meaning that we have a lot of 5xx errors. The next thing is the customer success rate is also on fire. The customer success rate is 0%. And we get a page. The on-call engineer is paged, receiving this message about the incident. So the first thing to do after we got a page is to go and check the alarm. The alarm dashboard is the CloudWatch alarm dashboard, contains the description. In the description, we have the guidance, what to do if this incident happened and how to navigate the problem, what steps to take. So this guide helps us to navigate, to go to the runbook, to check a specific section of a runbook, and take the actions after. Okay, so now once the game day is run, it's time to investigate the problem. So this is probably done by the on-call engineer. We go to investigate, we go to that runbook that was guided us on the alarm page. We check the symptoms, the runbook of course has the symptoms to see if this is really the same problem that we see. We can see that the system actually matches. Then we go over the root cause analysis checklist, which is some steps that on-call engineer should check in order to understand if that helps. And then the mitigation steps. During the mitigation steps, we have that link to the logs. And while checking the logs, I can see this interesting error, which is connect timeout on the endpoint. And the endpoint is DynamoDB VPC endpoint in the US East 1A zone. And this is kind of a problem because US East 1A zone is actually the zone which is impaired during this experiment. Then we go to the config file, which is the config file distributed to all the instances of the application. And we can see that this endpoint is actually hard-coded for all the zones, meaning that if the application exists in different zones, it will still try to connect to the previous zone. So this is a problem. Now let's go and conclude the game day and see what is the problem visually. So here we can see these 3 availability zones. The first one was impaired, and 2 other, even though they were healthy, they were still trying to connect to the DynamoDB VPC endpoint in the US East 1A, which was impaired. So it couldn't work. We never could reach DynamoDB. Probably one of the ideas to fix this would be to have intra-AZ calls and connect to the DynamoDB VPC endpoint to that zone where the instance is located. That is one of the ideas, of course. The game day probably would end with the ticket to the development team to fix the problem, then go through all the development process and release process of the bug fix. So this concludes the game day. And now we move to the continuous experimentation. So if you are happy with your ad hoc experiments and you want to have those experiments to be run on schedule, you can do scheduled experiments. And this feature is available in the Fault Injection Service. I will show a quick demo after. Then the chaos pipeline. So you probably don't want to you probably don't want to add the experiments in your release pipeline because maybe you want to give a sufficient time for the experiment to be executed. And also, maybe you want to run those experiments on different workloads than those that are in your release pipeline. So for this, you can use the separate chaos pipeline. And the last but not least is the on-call rotation. In AWS, we have this secondary on-call who periodically runs the game day in order to test that runbooks are up to date, that the operations are fine, and the on-call can sufficiently follow the runbook to fix the problem. And here is the quick demo how to schedule the experiment with the FIS. This is the experiment template that we used for the game day. We have this schedule stub. We just create a new schedule. We give those schedule a description, and then we configure the rate with what we want this experiment to be run, how frequently we want it to be run. Let's say we want to be run every 24 hours. Then we configure the start and time, we give permissions, and here we are done. The experiment now runs on schedule. Okay, so this is it from the demo part. And now I would like to invite Lex from BMW to share their chaos engineering journey. Thank you.
Yeah, I hope that all of you are enjoying reInvent same as we are, and I hope that first 2 parts were interesting for you guys. So my nickname is Lex, but my actual name is Croatian, a bit confusing to say, Hrvoje. So I'm Hrvoje Lukavski, coming from BMW Group. I am the architect and product owner on connected vehicle platform, and I'm responsible for CI/CD offerings there. So let me share with you some of our insights. You know that we at BMW are very passionate about speed, about performance and driving pleasure. I hope that most of you heard our Freude am Fahren sentence that we advertise a lot, which means driving pleasure. So as we are more and more becoming the software-driven company, we also want to translate this passion that we have for the cars into our digital offering. And this is why you can see on the slide that we have many cool services offered, such as video streaming in the car, such as location services, or the remote software upgrades that we are performing. So there are many more that couldn't fit here. These were just ones that we would like to highlight today for you. And I would like to share with you some numbers so that you can see that these services are quite complex and they require really perfection in terms of the connectivity between the car and between our backends where we host all of these services. So let's jump to it. So Around 20 years ago, we have released first connected vehicle. Today, we are operating a fleet of more than 23 million connected vehicles. On daily basis, we are upgrading over the air more than 9 million vehicles worldwide. 23 million plus vehicles is the largest fleet of connected vehicles globally on planet Earth. These upgrades that we are performing on daily basis, they amount for 197 terabytes of data a day and 14 billion requests daily that we have to process. And now you're getting the sense why reliability is very important to us and also why resilience is important to us, but we will get to that as we go on. We are having more than 1,300 microservices that are scattered across 100 AWS accounts. And today we have around about 99.95 reliability, and we want to keep it there and make it even higher. So let's jump into the next slide. That was like 4 years ago, yeah? So around 2020, we have performed our first on-premise chaos experiment. In our on-premise chaos experiments, there was a guy that was pulling the plug from the wall to test its resilience and failover capabilities. So that was really fun. It was go live, and there was a guy that would pull the plug from the wall. Of course, as we migrated from on-premises to AWS Cloud, somewhere around 2023, we had to identify the critical components because, as you can imagine, our architecture has changed plenty going from the on-prem to the AWS Cloud. While we were identifying these components, we were thinking, how can we replicate this again? So what's the solution? How can we pull the plug but in the cloud? So we needed something more sophisticated. This is where we found out about AWS Fault Injection Service that is offering a blueprint called AZ Power Outage. So that was a perfect fit for us, and we decided to proceed with it because it's literally mirroring what we were searching for. Today, we have performed successfully 11 chaos experiments in production, and actually in 2025, our plan is to increase this by factor of 10. So we want to have hundreds of chaos experiments happening in production. And if you are wondering how we want to achieve this, basically we will try to automate and give service owners capabilities through the portal to choose the experiment that fits their need, and we are going to execute hundreds of those smaller experiments that they would like to have in their environments. So this is showing why we do what we do, reflecting that 99.95% of reliability. Before we jump into customer account and our architecture of one of the accounts, I would like to share with you a little bit about our platform. So we have a cloud developer platform that we call Orbit. This platform is a central building platform for all development teams. And this gives us possibility to boost stability, to increase resilience. With every update or anything new we bring, we are affecting all of those 1,300 microservices centrally. This makes it that stable. This platform consists of something like is my part CI/CD, or from other colleagues like analytics and logging, compute and networking, and some others. We didn't even have, of course, space to put all of them, but this is just to give you the sense of what's going on there. So success of this platform is crucial for us because all of our backend services rely on this platform, and that is why we invested a bunch into doing chaos experiments, because we want to investigate all the edges, we want to know all the corners well. We don't want to leave anything to the case. Let's now jump into one of the usual AWS accounts, as I mentioned. So here you can see on the sides, this is one of the usual customer AWS accounts, and it consists of Platform VPC and Product VPC. Platform VPC, there we are using EKS service for compute across 3 availability zones. EBS volumes are used for caching. We are hosting here third-party binary management system. In the product VPC, we have Amazon Aurora for persistent data layer, and this is usually operated by service owners teams. We are using Postgre Amazon Aurora for increased failover capabilities and resilience in multi-AZ mode. What we have performed here is the AZ interruption experiment that I mentioned. So we decided to impact all the services that are hosted on the platform in one availability zone. So what we found out is that more or less everything went well, beside one thing. We have observed the very known limitation of EBS volumes that are zonal services. What happened is that our cluster started recovering in other two healthy availability zones while bringing new nodes and new pods into healthy availability zone. Our volumes were still bound to the different availability zone that was impacted. And this introduced the application errors, and our third-party binary management system operated 15 to 20 minutes in suboptimal state. It slowed down heavily until recovered. And this gave us the opportunity to fix the things that we found out during this experiment. So we were able to proactively find this, fix it, improve it, overcome the issue, increase our resilience, increase our stability, and when this happens again, we won't have any issues. So handover went much smoother afterwards. Now let me show you our second example from our pocket that we prepared for you, which was also very, very cool one. So here we are talking about MQTT. So communication between the cars and our backend services, as mentioned, is through the MQTT service. So it's really crucial that this MQTT service operates well and stable without any hiccups. We are using for MQTT off-the-shelf software product. This off-the-shelf software product is hosted on EC2 instances across 3 availability zones that are creating sort of interconnected cluster that is processing all the messaging requests. MQTT in BMW is also used for remote service requests, vehicle telemetry, and similar. So let's pull the plug once again and show you what happened with MQTT. So with MQTT, we have decided to use experiment where we terminate all the resources in one availability zone and we prevent their spin up in the same availability zone by injecting the insufficient instance capacity errors. While performing so, everything went more or less as expected, but in the case of high traffic especially, we have observed delays, retries, and this becomes very dangerous. When you think of the fleet that I was talking about, the number of requests that are flying in, so any delay is really not acceptable. So what we've done, we have pointed out this to our software provider that we are using, as mentioned, for the MQTT service. They have been really plenty helpful, and we work together on optimizing the solution because due to default configuration of the software resulted in some unsuspected or unexpected situations. Once we fix the issues with our software provider for MQTT, we have repeated the experiment and we have observed that handover between the availability zones was much better and everything went smooth as we expected actually the first time. Something that I find really important, and I think this is the most valuable part to share about BMW story, is the lessons learned, of course. First one that is really important is cross-team collaboration. So we found out that knowledge sharing, workshops, and also coordinating different teams, putting them together, different departments, really boosted the chaos engineering initiative that we were striving for. Second thing that we saw that is really crucial to have leadership buy-in, because when you try to do these chaos experiments in production, you have to have leadership support. It's not as simple as it seems without their support. And the third one that I would say is the most important one is the psychological safety. This is for sure, in my opinion, the most important learning. So I would propose to all of you to invest in environments where you don't have fear of failure, where failure is looked as the opportunity to learn, opportunity to improve. So my advice is that you start small, build confidence with smaller experiments on lower environments, and while doing so, slowly proceed to the production, and then use something very complex as AZ power outage, which is the most complex one offered at the moment that we have executed internally. So by radically rethinking our ways in BMW, we were able to move from pulling the plug out of the wall to having a sophisticated chaos experiments in the cloud. And this was exactly what we were searching for. And this, combined with psychological safety, cross-team collaboration, and leadership buy-in, really boosted what we tried to achieve here. There is a great quote from our VP, Celine, that said it really nicely. So this was truly a transformative journey for all of us. And we don't plan to stop here. We are committed now to take chaos engineering to a whole different level with everything that we've mentioned using automation. So remember these findings that we had, because I would be also very happy if I known them in advance, but we were learning on the go. In case you are interested to learn more, because we are limited with time here, we have a blog post that we have released. So AWS colleagues and BMW together in collaboration. It is exactly about the part that I'm presenting to you here. So please feel free to scan the QR code or check the slide deck later if you didn't have time, and read it. You will find more insights there. And also we will be around here after the presentation for any questions that you have. So yeah, I wish to thank you all for your attention. I hope you learned something from us, and remember that journey is the destination. There is no end point. It's just the small increments, especially in chaos experimentation. So I wish all of you in the room and those that are watching us best of luck on your journey, and thank you very much. It's been an honor. So back to you, Adrian and Juliana. Thank you.